Well, welcome everyone that's turned up tonight. For those that are guests, visitors to the ESR, please visit our website, esr.org. I'm having a mental block,
.nz.
esr.org.nz. Um, and if you want to get on our email list, because we do a presentation like this on the third Wednesday of every month, um, go onto the website and you'll find a place there where you can enroll for it. And now to introduce Godfrey. Many of you already know Godfrey, but Godfrey wasn't born here. He was born in Buenos Aires, a fifth generation Argentinian. His father, a civil and mechanical engineer, brought his family to New Zealand when Godfrey was only 10. And our thanks to the father. Godfrey grew up in New Zealand. He was educated here. He graduated here. He married here to Crystal Beavis. And together with Crystal, brought up two children here, their daughter, now an anesthetic technician, and their son, a mechatronics graduate, now a software engineer. And Godfrey, in his time, certainly made for himself a full and worthy career in engineering. The summary in the flyer is barely adequate, with so much left out. But for all that, Godfrey is not yet done. Here and now, he wants to tell us about his voluntary role in the University of Waikato's Research and Development Battery Group as its commercial lead. So without further delay, let's hear what Godfrey has to say. Thank you, Godfrey.
Right. Well, thank you very much. So, this is my presentation, and the first point I'd make here on this title slide is that we're calling the battery group the Revolutionary Battery Management Group, and that name took some thought and care because most of the group are scientists, and as a marketer and a business person, it was very easy for me to like a word like revolutionary because it really implies distinction. But the scientists who are involved in my group are much more careful and cautious about this, and they too like the word. So I think that sets the scene for something to me that is really quite powerful. And we'll go on to the next slide, which basically discusses what revolutionary battery management have got to do with engineers for social responsibility. Well, the first thing is, of course, it's engineering skills. It has lots of technology in it, so it's very much for engineers. The second point is that it really does improve the efficiency of the use of batteries and therefore reduces carbon footprints. And, for example, by facilitating use of batteries in EVs, and it also makes a big impact on energy systems that are electrical and that are varied by climate, such as PV and wind. And of course, if you use something more efficiently, you're going to reduce its pollution certainly from underutilized batteries. And we believe we have a lot to add there too. And perhaps going to the more human element, if at the moment pacemakers get replaced too early because the consequences of placing them too late are dire. So if you can know and understand what a battery is doing, you can clearly, with greater confidence, then you can, obviously you're improving social responsibility. So this is my webinar plan. Please interrupt. It's a bit difficult with the Zooms, but
Yeah,
if you put your hands
on the
up
back seat.
or something, someone's talking, by the way. I don't know. Someone's got their microphone on. If you do want to interrupt or do anything, by all means do so. It is more difficult in Zoom. But I'll be talking about this invention. I'm very conscious that this is a one-way thing. So if any interruptions, make it a little bit more interesting rather than just one person going on and on and on. But it is a bit challenging with Zoom. So I'm going to cover very briefly where this invention came from, the world as a need for batteries, the potential collaborations, a bit on the technology for the engineers, perhaps some of you electrical engineers, a discussion about the team, and question and answers if you haven't seen them. So quite clearly, sorry, questions and answers if you haven't managed the question. Quite clearly, we are talking about measuring the battery state, the charge it is now, and the health, or how warm it is, or its projected life. It arose out of the work of Professor Jonathan Scott, who is present with us tonight, and it started from electrode work that he did in neuromodulation, and that sounds fascinating to me. I have not had time to quiz him about it, but since about 2019, Jonathan and his team, Michael Cree and several others, have established a laboratory, and they basically got a bit of software, hardware, electronics that can measure the state of charge and state of health in normal use. Now, that's very important. The word in normal use is very important because, of course, this started in the lab, and now we want to make sure it's practical and useful to the real world. So they had to do work to make sure that was possible. They believe it's possible. We've got more research work to prove that it's possible. So we're definitely looking for research funding from either government sources. Everyone in research is always looking for funding, and this is one of my roles, and all of the government or the private sector. And obviously, the software and the hardware and whatever we're talking about can reside in the battery management system that most batteries have, from the smallest to the smallest one in the drill that you use, through to all the implanted battery in your pacemaker, all the way through to the multi-million-dollar spent on grid solutions. So the research is also going to look at not just lithium ion. There's been an obvious focus on that because of so much effort has gone into that and such a large proportion takes place. But it's, if we're going to be successful, it's critical that we have good collaborators and funders who are innovative. So again, that's one of the call outs for this webinar, as well as for everything I do actually. So why are batteries important? Well, I mean, this is stating really the obvious. They store energy when it's not used and release it when it's required. And the transition to a low carbon economy is going to make this really, really important. You can, clearly this says, there's a link there. So there's a 10-minute interview by me today with Jesse Mulligan, which covered some interesting. Jesse is a really good interviewer. I really like him, and for me it went very well. So you have that. So why do we need batteries? Well, you all must know the situation as it comes to climate change. This diagram is about a year old, but it's important because it shows that a year ago we were pretty close to the Paris Agreement Accord, and it's showing the different effects of the 4 different plans of action that take place. And you can see this is sort of what's currently in place, and this is the optimistic. So, and clearly batteries are going to have a really big impact on it. If you look at the latest United Nations framework convention on climate change, they're basically saying in 2023 it was 86 gigawatts of batteries, and they are predicting between, I can't see this, between 360 to 900 gigawatts. So that's quite a big amount. And of course, part of that is because batteries have decreased by as much as 89%. There are reports after reports on all of this. We're hoping to have this information up on a website, which will make it easy to understand and refer to. The leaders, of course, are China, who commissioned 23 gigawatts, United States 8 gigawatts, and European Union 6. New Zealand has about 42 gigawatts of power in total. So that gives you a feeling for, the amounts we're talking about are much greater than the all of New Zealand, but for battery. And finally, they're very much accepted by everyone as a key systemic enabler to remove our carbon footprint, to reduce our carbon footprint. So here's a picture of the battery deployment for power. This is for BESS. That's battery energy storage system, BESS, as it's known in the electricity industry. And it shows, 23 gigawatt hours going to 92.3 gigawatt hours of energy. That's not power, it's energy. But anyhow, 4 times growth, which is 300%. And the Boston Consulting Group has made the important point that although 82% of New Zealand's electricity is renewable today, and by the way, today was, I think, 2022, which is a little bit old for us because everything's moving so damn quickly. It's probably about 85% now in New Zealand. But the important point was that
hasn't changed. Hasn't changed.
It hasn't changed. Okay, thanks, Thomas. So the important point is that total energy consumed is not the same as electricity, and a large portion of the non-renewable energy used in oil and petrol and diesel is used for transport, and hence, this picture that again is a year or two old, year and a half old, shows where the number of cars, EVs, are growing. The blue is the true EV, and the green is the hybrid, which will eventually be overtaken by blue because it's got an internal combustion engine as well. So that's in New Zealand. For our collaborators, the only battery generator in the country is 35 megawatt one, owned by Well Network, which is our electricity company here in Hamilton. And they are very close in Huntly. And they use SAFT batteries. And as I was mentioning before I started the meeting, SAFT batteries are now being used in 3 of the 5 battery generating stations being built in New Zealand. And the only existing one is the one here, and that I've shown the photograph at the top. And it's rather interesting and unique and is ideal for us to work with because they have an engineering interest. And in fact, there's someone on Matt Jones is on this webinar, working for Power Electronics. And they, with Infotech and Well Networks, are actually operating this battery and understanding how to better get the best use out of it. And of course, the fascinating thing is that there's quite a lot to learn. Although batteries are an age-old technology, we're actually quite in the steep learning curve about how to use these modern batteries in the large applications we're talking about. So this is me personally speaking. I believe our group has a huge amount to
your
add. Someone else needs to turn their, is it Nigel, needs to turn their speaker off, microphone off, because this Infratech and Well Network are getting deep inside and understanding the battery. Whereas, again, this is my understanding from a role that I'm really have only been doing for a year as a volunteer. The big companies like Meridian, Contact, Genesis are relying on a contractual, this is a very sensible approach, by the way. When you're spending $100 million on a bit of equipment, you then pin down the supply with a contract, and you're not so worried about the operational aspects. But this is why Well Networks and Infratech are such good potential collaborators for us, because they are really interested in understanding the inside of the battery. So the other collaborator we've got is Transpower. They were our first. I approached the chief executive when she gave a speech here at the University of Waikato, and she was very delighted. She was the chief executive, Alison Andrew, and she was really helpful in putting me in touch. And now we're working with their very, I think that he's a very senior engineer reporting directly to the chief executive, or he was then, and I still think he is now. So he's a sort of like a troubleshooter. And we're working on lead acid batteries for the Transpower. Now, Transpower are the grid operators, so they can't get involved in the battery project that I've just told you above, but they have 174 substations, but they're very, very keen to have going 100% of the time. So they've got 2 battery packs, but they're lead acid. On one hand, that's more challenging for us, but on the other hand, it's a greater opportunity for us because, you know, the world has many more lead acid batteries than just about than anything else. So, so that's another very interesting point. So here is a table of BESS in New Zealand. I mentioned to you there were 5. Actually, there's more than 5. There's 7 there. 1, 2, 3, 4, 5, 6. BESS being planned, battery energy systems being planned for the grid in New Zealand, and one of them, of course, is actually working. That's the top one. And you can see over here, there's Meridian Energy. They say they're going to be ready in early 2025, and Contact Energy by March 2026, and Genesis Energy by the fiscal year 2027. So we're talking about, you know, really imminent applications of this important technology, and we believe we can help in all cases. So the other collaborators are a little bit more high-tech in a different way. Gillian is a lithium sulfur battery manufacturer that has really interesting potential, and we're basically collaborating with them so that they can use our models to see if it works with their technology. Allegro is a company that makes flow batteries, and that's a totally different type of battery. Instead of being static, you're actually flowing. It's a bit like a petrol engine, but instead of a petrol engine, it's a battery. So that is another. And SolarSense is a less high tech, but it's still very interesting to us because they're suggesting we put in a solar PV system in the university so that we can actually monitor the battery and so on and so forth. All these things are helping us acquire data for real world applications that really most people have been guessing at in the past, or what is important and what isn't. I mean, everyone knows voltage and current are clearly, obviously important, and time. But if we have a model that actually uses this, there are different emphasis that comes on it all. A quick pause in case anyone wants to ask me anything. Okay. So to quote our draft research funding, we're applying, of course, for research funding from all sorts of different sources, but from the government and collaborators where they can afford it. And we're basically, this is A, B, and C. This stuff, I'm afraid, I couldn't explain to you other than well, I will be explaining a tiny, tiny fraction of this, but we're using fancy maths, fancy circuit models, and fancy wavelet analysis. And the result is that we revolutionize method predicting bacterial and progressive aging. So this is the number of our claim, and it's quite exciting. This is the digital twin, and we're basically saying we're going to benefit New Zealand in a big way. One of the points that comes across is that measurement of state of charge, SOC, and state of health is sort of taken for granted that everyone can do it, because you all want to know what's in a battery, and you all have a dial that says the battery is so many charged. If you got I was talking to Jason Mulligan today, and he said, well, he had an electric lawnmower and he pressed the button and it went up to 5 lights. And if they had 2 lights, he knew he better recharge it. Well, the consequences of that are actually minor, and getting it wrong by any, even 50%, getting it wrong by 50% isn't particularly critical. And the lifetime of a battery in those circumstances isn't particularly critical either. So, if the battery wears out in 6 years, or let's put it, say, wears out in 3 years instead of 6 years, well, you'll feel a little bit annoyed, but, who cares? And you're not going to be rushing off to claim guarantees. On the other hand, if you're running a big $100 million battery power station, you certainly are. And hence my earlier comments of relying on the contract or relying on better understanding. And so what Professor Scott has said here is that basically, the consequences of being inaccurate in these areas have not really hit home to us. And I would say that this research project is now going to have its time in the sun, because suddenly we are becoming to know that batteries are going to be much more important to our future than any time before. If we'd tried doing this 10 years ago, I think, maybe it would have been different. So here's a little bit for you engineers. Most of you know that DC current coming from a battery will go through a resistor or a lamp, and you measure the resistance or the impedance by measuring the voltage divided by the current, and that's measured in ohms. However, if you plug into the wall, you're getting AC. So alternating current is more useful than DC current in many senses of the word, because you're able to transform it from the hydropower station or the geothermal thermal station up to thousands and thousands and thousands of volts, send it along the cables, and then transform it down again to 230 volts into your home. Now, when you're doing that, it's an alternating current. It's 50 hertz, but wherever you look at frequency, alternating frequency, you've got to start being clever, much more clever than the DC resistance. And here we have what I think is the sort of the heart of the science that we're talking about. So down the bottom, we have frequency, and on the far left, we have days, and on the far right, we have seconds. Well, 10 to the 0 is 1 second, so it's 1 hertz. And over on the bottom left-hand corner, well, actually, no, on the band going up from 10 to the -3, all the way up there, is not being measured by hardly anyone, if anyone. And our scientists have measured it, and we're discovering really, really useful stuff. The equation that describes a battery can be shown up above there, and there's the squiggle lines are resistance. Those, remember, are simple resistance. And then the other elements are the strange looking, well, there's a capacitor in the middle of the diagram. If you can see my arrow, and I should try and, oh, anyhow. So that's a capacitor, which is a non-linear device. A resistor is a linear device. And over here, we've even got more non-linear, because these are fractional capacitors, or fractional, what they call constant phase. What's the constant phase? What's the E stand for? Are you there, Jonathan?
Elements.
Element. Thank you. Element. Yes. So this starts to describe this observation. So what we've observed fits in with this fancy calculation. Oops. Hang on. There we are. Fancy calculation. And the P1, P2, P3, this is an oldish diagram, and it refers to the patents that the team felt we could apply for, and still can, because we have not shown too much of the science. I mean, this doesn't give away any of the science, but what it does show is that the batteries behave in a way that's predictable according to this formula and graph. So, and here, this little picture here says no off-the-shelf instruments work below 1 millihertz. Okay, so you have to spend 50,000 and a lot more to start investigating the area to the left of this curve. So this next slides come from a presentation by Marcus Wilson, who may or may not be at the presentation here, but and you can see the other people on the team here at the metrology conference in Wellington 2 years ago, or 1.5 years ago, 2 years ago. I can't see because the picture's in the way. So again, this is a very simple slide reinforcing what state of charge is and reinforcing what state of health is. Now, this diagram shows how we started making those measurements to see that fancy diagram, which, by the way, electrical engineers call Bode plots. That did not include phase. It just included the impedance side of things, not the phase. Again, very, very electrical engineering stuff. But this is the device or the circuitry that measures what we were talking about. And it may be a simple block diagram, but it's $50,000 worth of detail inside. So, and that doesn't include the scientist's time. It's just, yeah, and there's a lot of that. So we're getting close to the end now, but this slide again reinforces the fact that the batteries are changing in this place here, which is 10 to the -5 hertz, which is 12 microhertz, which is once a day roughly. And from here all the way to a week to 3 hours, things are explained differently. One of the difficult things when you're measuring long times is that the ambient conditions change. And of course, temperature is one that's easy to understand. In physics and chemistry, everything changes with temperature. So you have to gather that information and make sure it's included in your modeling. Because a fascinating story that Jonathan told me, it was only a day or two ago, was that, you know, a scientist thought they'd discovered, a colleague scientist from overseas, not in our group, thought they discovered a trend, a very exciting peak in their graphs. And very quickly, of course, our experience told, that's the team's experience told their overseas collaborator that that was the air conditioning or day and night changes in temperature. And, these are the sort of things that clearly are need to be factored in. So, and it obviously takes weeks for you to get results. This is a big table, and I'm not going to comment on it except for the bottom one. And I'm just going to move that up to the side. So the bottom one is interesting because it's not, it's sort of history and social history rather than engineering. No, it's engineering history. So in 1897, a person called Phuket established that batteries, this was lead acid batteries, performed different according to their age and their temperature and all those sort of things in a certain way, and they discharge in a certain way. And he put an equation for it. And the funny thing is, since 1897, that equation has largely explained even lithium-ion batteries, but no one has understood why. It was just what they call empirical. It was just curve fitting, and there was no thing that went behind it. Well, the exciting thing is that our group has applied its modeling, and it explains Phuket's equation, by the way, in the area that Phuket never looked at, of course, in the area that we are looking, which is in the low frequency area. So that's just one of 7 achievements of our group that I think is very impressive. We really have, I think, a world-class team here, even though by no means are they recognized as being such, because, well, who the heck is Waikato University and New Zealand, for God's sake? We're not in the top. I did approach the top battery researcher used by Tesla, and his name was Dan. I can't remember whether it was Jeffrey Dan or something, but anyhow, he just wasn't interested, and well, understandably so. I mean, they've only got so much limited time, and we have this New Zealand challenge of breaking into world-type science. So I'm excited. I've got my credibility on the line. Of course, every one of us here has got their credibility on the line, and I've seen enough to be convinced. And you can see here, I've put everyone's email address there if you want to talk to us. We actually have a battery. Are you seeing the website at the moment? Someone give me a hands up. Yep. Okay. So there's a website here that shows us, including this is Jeff, your biography of me that I did a copy and paste, which is far too long. So I need to correct it. But and you can see that the website page here, we're getting ready to actually give information, but there's lots to go yet. Back to the PowerPoint. So how long has that been? Oh yes, that's more than half an hour. Oh no, we started late, so it's about half an hour. So would you like to ask me questions? I have 3 slides more. My contact details are there. There are my contact details, and they're also up there as well. And the key players are also here. And these are slides that I have not spoken to, but are there to be discussed if you want. I'll stop sharing and see how we're going.
Well, thank you very much, Godfrey, and getting your team to come. This has been a very fascinating presentation, and it set a very high standard for this year. And I'm looking forward to many more of them. Thank you, everyone. And Chris, good to see you, Chris. Done?
Thank you, Jeff. Good to see you too.
Okay, well, and thank you all for coming, and especially those from the other side of the world.
Hmm.
Thank you.